Imagine a world without computers, smartphones, or the internet. It sounds almost impossible today, yet all these technologies, essentially your entire digital life, are built on one element: silicon. This unassuming element is literally the sand beneath your feet and the rock in rock crystal. In an almost poetic twist, this same material that ancient humans used as stone tools and glass beads has become the backbone of modern electronics. How did a common element from the Earth's crust rise to such high-tech prominence? Welcome to Cube Chemistry, where we will discuss all the elements of the periodic system and also do experiments. So if you like this video and want to see more, make sure to like, hype, subscribe and hit the notification bell so you will never have to miss another episode. Now, no poll till the 6th of January, as we will go on a well-deserved break. But no poll doesn't mean no videos. We will keep posting new videos every week as expected. See you next year. Now, in its pure form, silicon is a hard crystalline solid with a metallic gray color and a subtle bluish tint. It doesn't look flashy at first glance, but when light hits it just right, you'll notice a clean, almost futuristic sparkle. This is the kind of silicon used in computer chips and solar panels, grown into giant single crystals, then sliced into mirror-smooth wafers. It's got a sleek, high-tech vibe of something straight out of a sci-fi lab, but it starts as something as simple as sand. So this is also what we see here in the cube. We see parts of what seems to be wafer pieces, and in this vial we seem to have more of that crystalline structure. Now it looks smooth, and that makes me wonder, can you lick it? So technically, yes, and that's also what the periodic leaking table is suggesting. Pure silicon is non-toxic and doesn't react with your saliva or anything inside your mouth. But before you go sticking your tongue on a silicon wafer, keep in mind it's brittle, really brittle. Those edges can be surprisingly sharp. Lick the wrong spot and you might end up with a slice across your tongue. Not exactly the most dignified way to explore chemistry. Yes, you can lick it. No, you probably shouldn't. What's even more common than pure silicon is silicon locked into compounds. Sand, quartz, glass, most rocks. These are all mostly silicon dioxide. You see it every day in windows, phone screens, and concrete walls. But while those materials are safe to touch, they aren't exactly snackable either. Inhaling fine silica dust, for example, can actually be dangerous to your lungs over time. So whether it's glass or quartz or some other silicate, the same rule applies. No licking. Silicon's got enough jobs already. It doesn't need to be on your menu. Now, the name silicon originates from the Latin word silex or silix, meaning flint or hardstone. Flint was highly valued by early humans for tool making, so it's fitting that the element inside flint eventually became central to cutting-edge tools of the digital age. Now, in the early 19th century, chemists suspected that flint, which is mostly silicon dioxide, contained a new element. In 1808, the English chemist Sir Humphrey Davy proposed the name silicium for this element to be. He chose the ium ending because he assumed it was a metal. Many elements like sodium, calcium have that ending. For a while, people informally referred to the elusive element as silicium. However, in 1817, a Scottish chemist named Thomas Thomson argued that the element's properties would be more like carbon or boron, which are nonmetals, so he tweaked the name. Thomson dropped the ium and coined the name silicon, with an on ending similar to carbon and boron. Now that's the name we use today, and as a side note, many other languages still call it something like silicium. For example, silicium in Germany, and in Dutch it's called silicium, but English settled on silicon. Now this naming history might seem trivial, but it hints at silicon's dual identity, part metal-like, part non-metal-like, a clue to its true nature as a metalloid. Now, one thing to clear up early, silicon is not the same as silicone. Many people confuse these words. Silicon is the element, symbol, Si, a hard crystalline solid. Silicone, with an E at the end, refers to a family of rubbery polymers, like the material in certain bakeware, sealants, or surgical implants. Silicone does contain silicon atoms, but it's a chemical compound, not an element. Now, silicon is so abundant on Earth that humans have been interacting with it for tens of thousands of years without realizing it. In fact, the Stone Age could just as easily be called the Silicon Age. Our prehistoric ancestors shaped flint and other silica-rich rocks into tools and weapons. Flint and quartz crystals are forms of silicon dioxide. When flint is struck against steel, it produces sparks. Early humans used this property to ignite fires. Little did they know, those sparks were an early cameo of silicon's chemistry at work. The ancient Egyptians, pre-dynastic period, were familiar with shiny quartz crystals, essentially pure silica, made of silicon and oxygen. They carved quartz into beads and small vases, treasures that have been found in ancient tombs. Now, the ancient Chinese also used forms of silicon-based materials like jade and pottery glazes in their artifacts. Moving forward to around 1500 BC, Egyptian and Phoenician artisans mastered the art of making glass. Now, their glass was made from sand rich in silica, mixed with other ingredients and melted. Clear or colorful glass beads and vessels from ancient Egypt are basically silicon dioxide that has been melted and cooled, an application of silicon compounds long before anyone isolated the pure element. Early construction also relied on silicon-based compounds. Ancient builders used mortar made from mixtures containing clay or lime and sand. Clay and sand are loaded with silicates, minerals containing silicon and oxygen. These mortars helped hold stone dwellings together. In short, silicon in the form of stone, sand, and clay was literally the foundation of early human dwellings and tools. Our ancestors didn't know about silicon as an element, but they took full advantage of its compounds, from spearheads and spark-making flints to the first glass trinkets. By the late 1700s, science had advanced enough that people started suspecting the existence of silicon as a distinct element. Antoine Lavoisier, the great French chemist, included silica, silicon dioxide, in a list of substances he thought were chemical elements around 1787. Lavoisier reasoned that silica might be an oxide of some fundamental element, just as rust was oxide of metal and iron. He tried to chemically reduce silica, essentially to break the silicon free from the oxygen, but he failed. Silicon's hold on oxygen was too strong for the methods available at the time. Modern terms, silicon has a high affinity for oxygen, meaning they stick together stubbornly. Lavoisier didn't have the tools to separate them, so silica remained a mystery substance in his day. In 1811, French chemist Joseph-Guy Lussac and Louis-Jacques Thénard gave it a shot. Now, they heated a compound called silicon tetrafluoride with molten potassium metal. Now, this reaction did produce something, a brown solid that was probably silicon mixed with other byproducts. Today, we'd call it impure amorphous silicon. However, Guy Lussac and Thénard didn't realize they had created dirty silicon. They couldn't properly characterize it as a new element at the time, so the credit for discovering silicon didn't go to them. Finally, in 1824, a Swedish chemist named Jöns Jacob Berzelius succeeded where others had failed. Berzelius used a similar approach to the French duo's heating a mineral called potassium fluorosilicate, basically a combination of silicon, fluorine, and potassium with potassium metal. And that reaction broke the silicon-oxygen bonds and freed silicon atoms, which Berzelius then painstakingly washed to remove all residues. The end result was a small amount of brown powder, pure elemental silicon, still in amorphous form. Berzelius examined this powder and recognized it as an element that had been eluding chemists. He is credited with the discovery of silicon as an element, since he was the first to isolate and describe it clearly. Berzelius even noted some properties. The silicon powder was a brownish metallic-looking substance that did not dissolve in most acids. Berzelius' success marked the official birth date of isolated silicon. Scientists now had samples to study. For many years, silicon was obtained only as an amorphous non-crystalline powder. Crystalline silicon, the kind with the shiny metallic gray appearance, was first prepared in 1854 by Henri-Etienne Saint-Clair de Ville in Paris. Now he used a chemical reaction involving silicon tetrachloride and aluminum metal to produce elemental silicon crystals. Another method around that time was electrolysis of molten salts containing silicon. These processes finally yielded silicon crystals, which were hard, shiny, and had an octahedral diamond-like structure. Chemists observed that these crystals had a metallic luster but were brittle. By the late 19th century, silicon chemistry was advancing. In 1857, Friedrich Wöhler discovered silicon hydrides, and in 1863, Charles Friedel and James Crofts made the first organosilicon compound, linking silicon with carbon chains. Silicon was revealing a whole repertoire of compounds, some similar to carbons, but many quite different, showing that silicon is not just a copy of carbon. So by the end of the 1800s, silicon was a known element, though it still didn't have any major uses. It was more of a chemical curiosity. Now, like mentioned before, if you hold a lump of pure silicon, assuming that you have it laying around, like we got in this vial, the first impression is visual. It's a dark gray solid with a bluish-silver metallic sheen. It almost looks like a metal, shiny like one, but not quite as lustrous as polished aluminum or silver. Silicon in crystalline form is actually quite beautiful. Large silicon single crystals are sometimes made for demonstration, and they exhibit a diamond-like sparkle on their facets. However, unlike true metal, silicon is brittle. Try to hammer a pure silicon wafer or crystal, and it will crack or shatter like glass, rather than bend. In fact, the internal structure of silicon is the same as diamond, pure carbon. Each silicon atom is covalently bonded to 4 neighbors in a tetrahedral arrangement, creating a repeating diamond cubic crystalline structure. This strong interconnected bonding gives silicon a relatively hard structure. On the Mohs hardness scale, silicon ranks about 6.5, which means it can scratch glass and is almost as hard as quartz. Not surprisingly, since quartz is silicon dioxide. But again, unlike a ductile metal, silicon will fracture if you apply too much force. Silicon's melting point is a whopping 1414 degrees Celsius or 2577 degrees Fahrenheit. That's extremely high, over 4 times the melting point of aluminum and about 2/3 that of iron. In fact, among common semiconductor elements, silicon's melting point is higher than many. For comparison, pure gold melts about 1064 degrees Celsius, so silicon would still be a solid while gold is a liquid. Now, the boiling point is around 3265 degrees Celsius, which is even more impressive. These high temperatures hint that silicon atoms cling strongly to each other in the solid. You have to shake them violently, a lot, to break them apart into a liquid or a gas. This also foreshadows why silicon devices can sometimes handle higher temperatures than other semiconductor materials. Now, the density of silicon is about 2.33 grams per cubic centimeter, a bit more than twice the density of water. That makes it denser than glass, which averages around 2.2 grams per cubic centimeter, but lighter than most metals. For comparison, aluminum comes at about 2.7 grams per cubic centimeter, copper around 9 grams per cubic centimeter, and iron weighs at roughly 7.9 grams per cubic centimeter. Electrically, silicon is famous as a semiconductor. At room temperature, pure silicon conducts electricity only very poorly. In fact, pure silicon is closer to an insulator at room temperature. Its electrical resistivity is extremely high, millions of times higher than a good conductor like copper. However, if you heat up silicon, it conducts a bit better, the opposite of metals, which conduct worse when hot. This peculiar behavior is typical of semiconductors. The term semiconductors means it's neither a good conductor nor a good insulator, but something in between. And we can drastically change its conductivity by adding tiny impurities or by changing temperature. Chemically, silicon is a little bit of a Jekyll and Hyde. On one hand, it's inert at room temperature. It doesn't rust or tarnish in dry air. Leave a piece of silicon out on your table, and it will basically remain the same year after year. This is because when silicon is exposed to oxygen in air, it naturally forms an extremely thin coating of silicon dioxide on its surface, basically a microscopic layer of glass. Now, the oxide layer passivates the silicon, preventing further reaction. The silicon is essentially wearing an invisible rust-proof jacket made of its own oxide. As a result, acids like hydrochloric or sulfuric acids don't bother silicon at all. Only a very dangerous acid, hydrofluoric acid, can strip away the oxide and attack silicon directly. Hydrofluoric acid is one of the few chemicals that dissolves glass and thus can eat away that protective layer. However, if you crank up the temperature, silicon becomes highly reactive, heating it up red hot in oxygen, and silicon will combust. Yes, it can actually catch fire in pure oxygen when hot, to form white silicon dioxide powder. This is a vigorous reaction. In essence, silicon loves oxygen so much that given enough energy, it will grab oxygen and oxidize energetically. Similarly, at high temperatures, silicon reacts with halogens, elements like fluorine and chlorine, to form silicon halides, for example, silicon tetrachloride. In fact, silicon tetrachloride is a fuming liquid that was once known as liquor of flints because it can be made by extracting chlorine with heated flint silica. With nitrogen, silicon will react at very high temperatures to form silicon nitride, a very tough ceramic, and with carbon, as we noted earlier, silicon reacts in an electric furnace 2000 degrees or higher to form silicon carbide, one of the hardest substances known, often used as an abrasive and in high-performance ceramics. Silicon sits in the periodic table, group 14, beneath carbon. Like carbon, it has 4 valence electrons, so it can form up to 4 bonds. But there are big differences. Carbon readily forms double and triple bonds. Think carbon dioxide or carbon-carbon double bonds in organic chemistry. Silicon, by contrast, is not very good at multiple bonding. The silicon-silicon double bond is unstable and hard to make. Silicon prefers to form 4 single bonds in a tetrahedral arrangement. This means silicon chemistry doesn't include a rich variety of long chain and ring structures that carbon does, which is why life is based on carbon, not silicon. Silicon can form long chains indirectly, though, by bonding through oxygen atoms. For example, in silicones, polysiloxane polymers, silicon atoms alternate with oxygen atoms in a chain, SiO, SiO, etc., with organic groups attached to silicon. But a chain of Si, for example, is not something you'll find in nature, and even in the lab, it's tricky. Another interesting quirk, in water-based systems, silicon mostly shows 2 oxidation states, -4 and +4. +4 like in silicon dioxide or silicic acid, and -4 as in silane or metal silicides. Silicon doesn't form a stable +2 or +3 state in water, and it doesn't do redox chemistry back and forth easily at normal conditions. Now this means silicon is kind of chemically stuck in either fully oxidized form, silica, or reduced form, silicon metal, and it doesn't cycle between those states without extreme conditions, unlike say iron, which can go between Fe2+ or Fe3+ quite readily. This property has implications if you ever dream of silicon-based life. In bases, alkaline solutions, silicon can react if conditions are right. Strong hot sodium hydroxide, for instance, can etch silicon, forming soluble silicates. That's one way glassware can get slowly damaged by very strong base. The silica in glass reacts, but again, at room temperature, neither acids, besides hydrofluoric acid, nor bases have much effect on bulk silicon. Now, one last note on the chemical properties. Because silicon can be doped with other elements, in the sense that it participates in chemical marriages that give it entirely new properties, like electrical conductivity. For example, adding a tiny bit of phosphorus, a group 15 element, to silicon, gives N-type silicon with extra electrons free to move. Adding a bit of boron, group 13, gives p-type silicon with holes, an example, missing electrons that act like positive charges. These doped materials are not different compounds, they're still mostly silicon, but the impurity atoms in the silicon crystal lattice modify its behavior. This isn't a traditional chemical reaction, but it's a chemical alteration at an atomic level that is absolutely central to how silicon is used in electronics. Now, if you're looking for silicon, you don't have to look far. It's everywhere. Silicon is the second most abundant element in the Earth's crust by mass. About 27 to 28% of the crust is silicon, just behind oxygen at about 46%. To put that into perspective, silicon is more common in the rocks under your feet than aluminum, 8%, iron, 5%, or any other of the well-known elements. It's literally one of the building blocks of Earth. However, you won't find pure silicon in lumps in nature. Silicon in the ground is always found combined with other elements, primarily oxygen. The most common form is silicon dioxide, which appears in nature as a mineral quartz, and its many variants. Clear, rock crystal, milky quartz, amethyst, agate, flint, opal. These are all basically silicon dioxide in crystalline or amorphous form. Now, if you go to the beach and pick up a handful of sand, a large fraction of those grains will be quartz, silicon dioxide. Others might be silicate minerals. Silicates are a broad class of minerals where silicon is bonded to oxygen and one or more metals. Common rocks are silicate-based. For example, feldspar, a major component of granite, is a silicate of aluminum and potassium. Mica is a silicate of aluminum and potassium with a layered structure. Clays are aluminosilicates. Olivine, pyroxenes, amphiboles, zeolites, all these are silicate minerals found in various rocks. Now, more than 90% of the Earth's crust by volume is made of silicate minerals. In simpler terms, most rocks are chock full of silicon, locked in a matrix with oxygen and other elements. Silicon is also common in the mantle, the layer under the crust. Mantle is made of silicate minerals rich in magnesium and iron, like olivine and perovskite forms. So inside Earth, silicon is a major component. Now, what about elsewhere? Well, in the universe, silicon is pretty abundant too. It's estimated to be the 8th most abundant element in the universe by mass. Stars create silicon in their later life stages. It's often said that the computer chips are made from sand, which is essentially true, though the sand has to go through quite an industrial journey. Producing elemental silicon on a large scale involves two main stages: initial reduction from silicon dioxide to crude silicon, and then purification to get high purity silicon. Now, the first thing we're going to discuss is carbothermic reduction, making metallurgical grade silicon. The first step is to extract silicon from its oxide form. The most common method is to mix quartz, sand, or quartzite, a form of rock rich in silicon dioxide, with a carbon source, usually coke, a coal product, or charcoal, and then blast it with extremely high temperatures in an electric arc furnace. Now, the furnace heats the mixture to around 1900 to 2000 degrees Celsius. That's about 3600 degrees Fahrenheit or more. At such temperatures, a chemical reaction occurs. The silicon in silicon dioxide is reduced as the oxygen combines with carbon to form carbon monoxide and some carbon dioxide. In simplified form, the reaction is this. Now, the carbon essentially steals the oxygen, leaving behind molten silicon. This process is called carbothermic reduction. The molten silicon collected from the furnace is about 96 to 99% pure. It's often called metallurgical grade silicon. Why metallurgical? Because a lot of this silicon, in fact the majority of silicon produced worldwide, is used directly in metal alloys, like adding to steel or aluminum. More on this later. At this stage, it's not pure enough for electronics or solar cells, but it's fine for alloying or chemical uses. Now, interestingly, to avoid wasting silicon as silicon carbide in the furnace, operators often add an excess of silica and sometimes a bit of iron. If iron is present, the molten silicon will dissolve some iron and form an alloy called ferrosilicon. Ferrosilicon, usually 50 to 80% silicon with the rest iron, is easy to cast into ingots and is handy for steel making. In fact, roughly 80% of the elemental silicon produced ends up as ferrosilicon alloy for the iron and steel industry. China is by far the largest producer of silicon, ferrosilicon. Its factories churn about 2/3 of the world's supply of silicon. Other big producers include Russia, Norway, Brazil, and the USA. If you've ever seen a giant shiny ingot being poured in an industrial video labeled silicon, odds are it's this impure silicon intended for alloys. There's also a smaller scale method, aluminothermic reduction, where aluminum is used to reduce silicon dioxide, similar to a thermite reaction. It's another way to get silicon metal. The reaction yields silicon plus aluminum oxide slag. This method can be used when very high temperatures are not feasible, but it's less common industrially than the carbon route. Now let's talk about the purification to semiconductor-grade silicon. Silicon from the furnace, while 98% pure, still has a lot of junk from a microchip perspective. 1,000,000 parts per million too impure. We need to get rid of metallic impurities like iron, aluminum, calcium, etc. Achieving 99.9999% purity, often called 6 nines or higher, is necessary for electronic devices, and actually even higher purity like 99.9 etc. 9 nines is standard for the best chips. How on earth do we purify something to 1 impurity atom in 1,000,000,000? The answer lies in clever chemistry. One common purification method is the Siemens process, developed in the 1950s. In this process, the impure silicon is first converted into a volatile compound, then filtered, then decomposed back into pure silicon. Typically, the crude silicon is reacted with chlorine or hydrogen chloride gas to form chlorosilanes. These are compounds like silicon tetrachloride or trichlorosilane. For instance, silicon tetrachloride can be made by chlorinating silicon, and tetrachlorosilane often comes as a byproduct from making silicones. These silicon compounds are liquid gases that can be distilled to remove impurities. Impurities either don't form volatile chlorides or form heavier ones that separate out. Imagine vaporizing the silicon into a chemical form and then distilling it like purifying alcohol, only instead of whiskey you're distilling silicon juice. After multiple rounds of fractional distillation, you get extremely pure tetrachloride or trichlorosilane. Next, you convert those purified chlorosilanes back into elemental silicon. One way is to react trichlorosilane with hydrogen gas at high temperature on a silicon filament. Another way mentioned in some processes is reducing silicon tetrachloride with zinc vapor. Either way, the chlorosilane is decomposed and pure silicon is deposited, typically in the form of polocrystalline rods or chunks. The pure product is often called polycrystalline silicon, or poly-Si, and it looks like shiny crystalline chunks or rods. At this point, its purity is extremely high, like 6 nines or better. This poly-Si is the raw material for making silicon wafers. For solar panels, sometimes this level of purity, 6 nines to 9 nines, is enough and can be cast into blocks. But for microchips, we go even further. To make single crystal silicon that you find in computer chips, the polycrystalline silicon needs to be formed into one giant crystal. The most common method is the Czochralski process, and here is how it works. You take a quartz crucible, put chunks of high purity silicon in it, and heat it under an inert atmosphere, often argon, until it all melts. Remember, that's above 1400 degrees Celsius. Then you dip a small seed of crystal of silicon in this molten silicon. The seed is a perfect crystal oriented in a specific direction. You slowly pull it upwards while rotating it, and as you pull, silicon from the melt solidifies onto the seed. And if conditions are right, it continues the seed's crystal structure. By carefully controlling the temperature and pull rate, you can grow a cylindrical silicon ingot, or boule, that is a single crystal, often up to 200 to 300 millimeters in diameter, 8 to 12 inches, and perhaps 1 to 2 meters in length. This looks like an immense shiny log of metal, but remember, it's not a metal, it's just that look. It weighs hundreds of kilograms. Now these ingots are then very precisely sliced with diamond saws into thin wafers. Imagine cutting salami slices, but each slice is a wafer of silicon, maybe 0.5 to 1 millimeter thick. Those wafers are then polished to make them ultra smooth, and they become the substance on which microchips are built. Another method for ultra-high purity single crystal is zone refining or float zone process. In zone refining, a rod of silicon is passed through a heating coil that melts a small region at a time. As this molten zone moves along, it carries impurities with it, leaving pure silicon behind where it re-solidified. Repeating this can push impurities to one end of the rod, which is then cut off. Float zone can achieve incredibly low impurity levels, even better than the Czochralski. Sometimes because the crucible in the Czochralski process can introduce a bit of oxygen from the quartz. Float zone silicon is often used for special high power or sensor applications. To give an idea of purity, the final silicon crystals for electronics are so pure that you might have less than one foreign atom per 10 billion silicon atoms. It's one of the purest materials humans can make at scale. As a fun statistic, transistor fabrication requires such purity that one could say it's easier to find a needle in a haystack than an impurity in that silicon crystal. One more real-world tidbit. The ultra-pure quartz used as raw material often comes from certain special mines. For instance, Spruce Pine, North Carolina, USA, is famous for having the purest natural quartz sand in the world. The sand from Spruce Pine is used to make the high-quality silicon for semiconductors. It's ironic that an obscure Appalachian town provides the key ingredient for Silicon Valley's chips. That town, miners dig out snowy white quartz that's 99.999% pure to begin with. A great starting point for the process we described. So yes, the silicon in your computer might have once been hidden in a white sand deposited in North Carolina before it was melted and refined into a chip powering your device. Silicon's most famous role is as the semiconductor material that enabled modern electronics, transistors, microchips, solar cells, and all the wonders of the computer age. This role wasn't achieved overnight. It was a journey of scientific and engineering breakthroughs through the 20th century. Let's highlight a few key moments and reasons why silicon took the center stage. Before silicon was king, germanium, the element below silicon in the periodic table, was actually the first semiconductor widely used. The very first transistor, invented in 1947 at Bell Labs by John Bardeen, Walter Brattain, and William Shockley, was made from germanium. Germanium transistors worked, but had issues. They were sensitive to heat, and their performance was limited. Silicon was harder to purify at the time, so germanium was initially easier to use. However, silicon quickly caught up. In 1954, Morris Tenenbaum at Bell Labs created the first working silicon transistor. That same year, a team at Bell Labs, including Gerald Pearson, Daryl Chapin, and Kelvin Fuller, demonstrated the first practical silicon solar cell converting sunlight to electricity. Silicon was showing its powers. A pivotal discovery occurred in 1955. Researchers Carl Frosch and Lincoln Derrick at Bell Labs accidentally discovered that when you heat silicon in an oxygen-rich environment, it forms a layer of silicon dioxide on its surface, and that this silicon dioxide could act as a perfect insulator and protective layer on the silicon. This might sound obvious now, silicon plus oxide, silicon dioxide, but the key was realizing this could be used beneficially in making devices. Now, this led to the development of the planar process, where transistors could be built flat on the surface of a silicon wafer and protected by a glossy oxide layer. By 1958-1959, engineers like John Ernie, Robert Noyce, and Jack Kilby actually used germanium in his first integrated circuit, but Noyce used silicon, were inventing the integrated circuit, essentially putting multiple transistors and components on one piece of silicon. So why is silicon so great for these integrated circuits? One huge reason: silicon can grow a native oxide, silicon dioxide, that is an excellent electrical insulator. This oxide can be used to isolate components and as a dielectric layer in capacitors, etc. Germanium's oxide, by contrast, is not stable. Germanium oxide tends to dissolve in water and is not a good insulator. Once the purification methods were worked out, silicon could be produced in large quantities relatively inexpensively. As the transistor was perfected and the microchip era took off in the 1960s and 1970s, silicon firmly became the dominant material of the semiconductor industry. So much so that the primary tech hub of the world, Santa Clara Valley, California, earned the nickname Silicon Valley in the 1970s because of the many silicon chip companies there. And the name stuck, and now Silicon Valley is synonymous for the tech industry, even though nowadays a lot of software, which uses no actual silicon, is what people think of, but it all ultimately runs on silicon hardware. Silicon's reign in the electronics continues today. Over 95% of all semiconductor devices, transistors, diodes, etc., produced annually are built on silicon. Now, there are a few specialized areas where other semiconductors are used, for example, gallium arsenide or gallium nitride in certain high-frequency or optoelectronic devices, but those are the minority. For your computer processors, memory chips, logic circuits, silicon is literally the platform on which the digital world is built. A modern microprocessor can contain tens of billions of transistors on a sliver of silicon no larger than a fingernail. The transistors are so small and densely packed that you'd need a microscope, actually an electron microscope, to even see them. This incredible feat is often described as Moore's Law, the observation that the number of transistors on a chip doubles roughly every 2 years. For decades, chip makers have been shrinking transistors' dimensions, and we've gone from chips with micrometer scale features to now nanometer scale features. Current cutting-edge chips boast features around 5 nanometer or below. That's just a few dozen silicon atoms across. Through all these developments, silicon has kept up. The manufacturing techniques like photolithography, etching, doping, deposition have all been refined to work with silicon wafers. Now, one might ask, are we reaching the limit of silicon technology? The answer is that we are reaching some physical limits of how small silicon transistors can get, and researchers are exploring other materials like using silicon in combination with germanium or 2D materials like graphene, etc. But so far, even with new materials are used, they're often used on a silicon platform. For instance, adding a layer of silicon germanium alloy in a chip to boost performance, or building photonic components on silicon. The concept of silicon photonics is also emerging, using silicon not just for electrons, but to guide light for super-fast data communication on chips, using infrared laser light through silicon waveguides. That's still an active research and industry area and might become more important in the future. Now, walk into a city and look at the buildings, bridges, and roads. You're looking at a lot of silicon, but in compound form. Sand, gravel, and stone are key ingredients in concrete, which is the most widely used construction material. Concrete is essentially a mix of small rocks and sand bound together by cement, and cement is largely made of calcium silicates, produced by roasting limestone with clay. When you see a concrete wall, think of it as a hardened mush of silicate rocks, silicon holding up the infrastructure of the modern world. Now, glass is another big one. Ordinary glass, like window glass or bottle glass, is primarily made of silicon dioxide, silica, with some additives like sodium oxide or calcium oxide to tweak its properties. So all the glass windows, glass bottles, fiberglass insulations, etc. are silicon in a transparent disguise. Special high-purity silica glass is used for optical fibers that transmit data as light across the world. That's the internet backbone. Yes, silicon makes the internet physically possible through optical fiber. Ceramics and whitewares also rely on silicates. Porcelain, tiles, bricks, they often contain clay, which is a hydrous aluminosilicate, and are fired to hardness. Stoneware, crockery, toilet sinks, lots of these are essentially silicone-based materials. Even the glazes on ceramics often contain silica. Abrasives and cutting tools. Silicon forms extremely hard compounds that are useful for cutting, grinding, and polishing. We already mentioned silicon carbide, also known as carborundum. It's nearly as hard as diamond and is often used as an abrasive. For example, sandpaper sometimes has silicon carbide grit or grinding wheels. Industrial saw blades and drill bits sometimes use silicon nitride or silicon carbide ceramics for durability. Now, silicon plays an important role in metal alloys. We talked about ferrosilicon earlier. Used in steel making. When making steel, silicon is often added in small amounts to act as a deoxidizer. It helps to remove oxygen bubbles from molten steel, improving the quality. Also, certain steel types, like transformer steel used in electrical transformers, have about 3% silicon added. That small silicon addition greatly reduces the electrical losses in transformer cores by changing the steel's magnetic properties, an invaluable tweak for energy efficiency. Now let's talk about silicones, the material often confused with silicon by name. Silicones are synthetic polymers where the backbone is silicon-oxygen chains with organic groups attached to the silicon. They can be liquids, silicone oils, gels, rubbers, or hard resins. Silicones are incredibly useful because they can remain stable and flexible over a wide temperature range and are generally inert and biocompatible. Sealants and caulks. That waterproof goo you use around your bathroom tiles or window frames is often a silicone sealant. It stays rubbery and seals gaps, and it doesn't break down easily with sun or water. Lubricants and greases. Silicone oils are used as high-temperature lubricants or hydraulic fluids. They don't gum up like organic oils can and can handle heat. Even the heat sink grease used in electronics to transfer heat from the CPU to a cooler is often silicone-based grease. Medical and consumer products. Silicone rubber is used in everything from bakeware, muffin molds, spatulas, to swim goggles, to wearable sports bands, to medical implants like breast implants, which are made of silicone gel inside a silicone elastomer shell. It's used for contact lenses. Some advanced contact lenses are silicone hydrogel, allowing great oxygen flow to the eye. It appears in prosthetics and many healthcare applications because it's generally body safe and doesn't cause allergic reactions easily. Now, silicones were developed in the 20th century, notably by chemists like Friedrich Kipling in the early 1900s and later advanced by companies like Dow Corning. They show how silicone's ability to form bonds with oxygen and organic groups can create materials quite unlike anything carbon polymers typically do. Now, we touched on solar cells. Photovoltaic panels are predominantly made of silicon. Solar-grade silicon doesn't need to be quite as pure as microchip silicon, but it's still very pure. But 90% of the solar panels in use are crystalline silicon type, either single crystal or polycrystalline. The rest include thin film technology like amorphous silicon, which is also silicon, just not crystalline, or non-silicon material like cadmium telluride. So silicon is also driving the green energy revolution by turning sunlight into electricity on rooftops and solar farms worldwide. Now, silicon is also being looked at for the next generation of battery technology too. In lithium-ion batteries, researchers are experimenting with using silicon as an anode material instead of the current graphite. Silicon can absorb a lot more lithium in the form of lithium-silicon alloy than graphite can, potentially allowing batteries to store more energy. The challenge is that silicon expands a lot when it takes in lithium, which can damage the battery. But if they can overcome that with nanostructured silicon or silicon composites, future phones and electric cars might have higher capacity batteries thanks to silicon anodes. So here's the silicon, the hard rock that became the hero of the high tech. Our entire digital life was built on it. And who knows what future innovations silicon will support? Whether it's more powerful quantum computers, better renewable energy, or something we haven't dreamed of yet. You can bet silicon, or perhaps its close cousins, will be involved. Next time you swipe your smartphone screen or turn on your laptop, remember to give a little mental thanks to the element number 14. A bit of flint, a little dash of stardust, and a lot of human creativity. Together, they gave us the silicon era. And as they say in Silicon Valley, powered by silicon isn't just a marketing phrase, it's the literal truth of our time. Now, we would like to thank the members that support our channel. Thanks for doing this, and we really appreciate you. Now, if you think we missed anything, tell us in the comments, and if you want to know more about an element that we use for solar panels, look at this video of cadmium next.